track it, but we can unmute them.
Sure.
Or we can mute them. I'm sorry, not unmute them.
Yeah. So I'm also the host because I see all the requests for in the waiting room. So if I want to mute them, I can also go to mute it. But I mean,
if you are presenting, I think you will
Track
not.
it,
Yeah.
but we can
Okay, so I turned on the YouTube on.
Yep, I just got it on my computer.
Yeah, for a while, Ted, you started echoing because you had both of them on. But now it's fine.
Yeah.
So people start coming in. So 2 minutes, 3 minutes, I think I'll open the waiting room.
So this will be the last talk for this semester. Are you going to have some comment in the fall?
Yeah.
Yes. We have to arrange those yet, but that's the plan.
So
Last time we started around middle of February or something.
Middle of September.
I'm face wagging.
Oh, maybe you're 6 months ahead of phase. You're not lagging.
Usually never ahead, always lagging behind.
Yeah. Yeah, I think this online webinar is very useful, in particular for me and for my student here. We're in a smaller university, we don't have a lot of, seminar speakers. So they can come to join this kind of seminar to open their eyes. It's very good.
Yeah. So Nadim is here. You overlap with Nadim, right?
Yeah, sure. We have quite a few years overlap.
Yeah.
Hi, Rodney.
Good morning.
Good morning, Ronnie.
You guys are meeting, you have to meet over Zoom, right? You don't get to see each other at Iowa.
We're going to sit in the same room.
Different buildings, yeah. At least, yeah. We've been together once, right, Ted? We met last month once in person.
Yeah, I think it was once.
Hi, Stanley. How you doing?
Very good, very good. Thanks for coming, Ronnie.
Yeah.
Are you still in Ames, Rodney?
Yeah. I'm grading my
No
final
meeting, just
project.
I don't talk.
I think I'm going to admit everyone.
Yeah.
So you'll soon be muted.
I'm writing the difference between spring and fall, just to make sure. So Stanley, I'm going to give a minute more, okay? And then we will, I see people are joining. When it reaches a steady state, I will.
And Stanley, you are muted right now.
Oh, sorry. Yes.
There.
Okay.
Yeah. Good morning. Stanley, are you ready? Can we get started?
Yes, please.
Very good. Good morning. My name is Balachandar. I am the one of the editors of International Journal of Multi-Phase Flow. I want to welcome you all for the spring IJMF Spotlight seminar series. Today we have the final talk for the spring session. In a few months, we will start the fall session as well. So I want to welcome you all, and I want to hand it over to Professor Heindel from Iowa State. He will chair this talk, and he will do the introduction and take questions and serve as the chair. Ted, you're on.
Thank you very much, Bala. Well, it's my pleasure to introduce Dr. Stanley Ling, who's an assistant professor in the Department of Mechanical Engineering at Baylor. He obtained his BS from Beihang University in China and his PhD at University of Florida. I believe he's one of Bala's students, so that's great. He also did a postdoc at Sorbonne in Paris. He is also an NSF Career Awardee and member of ASME, APS, AIAA. And his current research focus is high fidelity simulation and modeling of multi-phase flows, including atomization in sprays, droplet surface interactions, and compressible multi-phase flows, which he will talk about today. So Stanley, I'm going to turn it over to you. It's all yours.
Okay, thank you. Now let me share my screen. And
everything looks great.
Okay. And you can see my mouse as well, Ted?
Yes.
Okay, wonderful. First of all, thank you very much for the introduction. And I also want to thank IJMF for the invitation for me to give the talk. This is one of my favorite journals. As you can see, some of the works I'm going to present today will publish over there. So I want to give start my talk, give an overview of the research in my group. So I do computational research for multi-phase flows. We love to develop new numerical methods and implement them in a simulation framework, and use the tool we developed to investigate fundamental multi-phase flow physics. And this knowledge we learn from the physics, we try to make use of them to innovate new multi-phase flow control techniques. And there sometimes is an application, it's a new application that require a new tool, a new method to develop. So we will spin back to the first step and develop the tool, and then and use it to simulate the flow, understand the physics, and keep going on. So this is general my philosophy in doing computational research for multi-phase flows. And since I focus a lot on computational research, I need to work with a lot of collaborators who focus on experiments and some modeling as well. And in particular, I want to acknowledge 3 collaborators: my PhD advisor, Professor Balachandar, and my postdoc advisor, Stephen Zarsky, and also a longtime mentor in my research, Greta Twophase. I know it may sound a little bit cheesy because they may be sitting in the same Zoom meeting right now, but they have impacted a lot, guided me into the area, and also have impacted a lot how I perform my research. And also, I also want to acknowledge my students and postdocs, including those who have graduated and those who are working with me right now. I come up with crazy ideas time to time, and they are the ones to make them happen. And the work I'm going to present today mainly performed in Dao Zhang's PhD thesis. So he has graduated and working in a consulting company right now. And Tangena is a student; she's continuing to work. And some of the research work we are talking about are done by her and also some other PhD students in my group. So this is the outline of my talk today. So I will first give a background about atomization and what kind of atomization problem we're doing. and I will give a brief introduction of the simulation methods we use. Some are more conventional approaches. I just quickly go through them, and something is the more recent that we developed, I will explain a little bit more. And in results, I'm going to talk about two topics mainly today. And the first one is I want to talk about spray formation and from the two-phase turbulent flow generated, what the statistics look like and why this is important. And the second part is more the subject of the topic today is I want to look at if I have turbulence at the gas inlet when we in the injector or in the nozzle, what would that impact the spray formation and so on. And finally, I'm going to summarize the key findings and also try to use a couple slides to project to the future what we are trying to do. So the atomization problem of our interest is called Airblast Atomization. So we know that if you want to burn a liquid fuel efficiently, you need to inject the liquid fuel in engine. And so atomization is the process to break the bulk liquid into small droplets. So you can choose to just inject the liquid itself. But if that's the case, typically you require a large injection velocity, injection pressure to achieve the high Weber number, Reynolds number to have an efficient atomization. One way to reduce the injection pressure and make the atomization more efficient is that you not only inject the liquid, you also inject the gas simultaneously. So this is called a twin flue atomizer. So Airblast is one typical, very commonly used twin flue atomizer. So you have a co-flowing, as I saw in this movie, thanks for Ted making a nice movie. So you have the liquid injected at the center. You also have the high-speed gas on the other side. So you can imagine the shear between the gas and liquid is pretty high when at the interface when the two phases meet. So this will enhance the atomization process and reduce the injection pressure. And the air coming together with the liquid is also useful for the combustion because this helps the fuel, vapor, and air mix together. So this Airblast atomization sometimes have cylindrical, that the orifice for the liquid come out is a circle, or they can also have a planar configuration like I'm showing in these two figures. So the planar one will be that what I am focused today. I will be focused on today. So for the planar atomization, there is something called a prefilming, that you have a liquid film forming on a plate, on a nozzle plate, and you have high-speed gas flow from both upside and down. So the shear will happen only on the top surface. And there's another configuration is that you have a planar jet, and the high-speed gas coming also from top and bottom, and you share the liquid interface from both sides and destabilize it and atomize it. So no matter which kind of planar Airblast atomization, the two-phase mixing layer is the key, and really the key of the atomization process. So this is a schematic showing what the two-phase mixing layer we're talking about. So you have a gas on the top of liquid. The gas velocity is higher, so you can see the arrow is longer, and the interface become unstable and forming the wave. And if you do the time averaging of the volume fraction, you will see that you see a typical kind of mixing layer that's growing spatially, gradually, like in a single phase flow. So a lot of complicated flow physics are involved in this process. The first, you see from this experimental video obtained by Matas et al. And you forming the longitudinal instability due to the shear. And the instability will not initially is kind of like a 2D, but later on they will become three-dimensional. You showing the transverse variation showing up, and then the liquid sheet is going to form and they're going to roll and become very thin and break in form droplets. And downstream here, the droplets mix with the turbulence and disperse away. So Below is the simulation we have performed, and we're going to talk a lot about this simulation and give you details later. But mainly that we have been inspired by the experimental setup, and so we use a similar geometry and setup to capture the whole process of a two-phase mixing layer and how sprays are formed in the two-phase mixing layer. So the overarching goal of our research is to perform a high fidelity simulation of spray formation. And the goal is to identify the dominant mechanism that has to lead to the spray formation. We want to characterize the two-phase turbulence and sprays. And one of the purpose of characterizing the turbulence and the sprays is try to see if there's a better way to simulate the process. Instead of using many cells and very fine mesh, can we develop a more like LES, like subscale models to simulate atomization process accurately, but also simultaneously efficiently. And with the tool we develop, we will be able to also to investigate new geometry and new atomizer that can do a better job than the conventional Airblast atomization. So again, this is a general philosophy of my research in my group. So now I'm going to move on to simulation methods. So to simulate the atomization process or the two-phase flows, we use the one fluid approach. So what that means is that we only solve one momentum equation for both phases, so treat them as one fluid. In the computational cell, you have interface, so basically change from liquid to gas or gas to liquid, and that's where we chase by solving the advection equation for the color function. So the color function here, we just simply set the 0 as a gas and 1 to be liquid. So if you look at the computational cell with half gas, half liquid, the color function will be 0.5. And we can compute any transport property or density on those cells with interface with the arithmetic mean. And these methods have been very well documented in the textbook by Greater and Ruben Scaldavari and Stefan Zaleski. So I'm going to use the open source flow solver called Paris Simulator for the simulation I'm going to talk about today. And in this Paris code, we solve incompressible variable density NS equation of surface tension. And it's a final volume method based on staggered grid, second order in time and space. And we use the VOF method, it's geometric VOF method, but we in particular use a new improvement that make the mass and momentum advection consistent. And we need to solve the Poisson equation for the pressure, and we have both the in-house multi-grid, but a lot of simulation I'm showing here today, we actually use the hybrid library. For the surface tension calculation, we use the high function method for the curvature and use the balance force discretization so to reduce the parasitic currents at the interface. And we have also developed a two-way coupled Lagrangian point particle model in the code as well. So here's the problem description. So we consider a very simple geometry. So one rectangle box here, and the turbulent gas stream coming from the left, and also the liquid stream in parallel. So as you can see, when the gas stream come in at the high speed, you're going to form a liquid gas mixing layer. For the injected gas in the stationary gas originally in the box, you have a gas-gas mixing layer. So the wave will become unstable and break and forming droplets. On the background, I'm showing the Z vorticity component. So you can see the flow downstream here also become very turbulent and mix with the droplets. So the gas stream height at the inlet, we call H, and H is about 0.8 millimeter. The liquid phase pretty much is water, but we have considered the gas to be a compressed gas with higher pressure and viscosity. And the surface tension, we do not use exactly air-water value. And the reason is that when we cast this number into dimensionless parameters, we have a nice rounded number. So the dynamic pressure ratio, the density ratio, and the viscosity ratio is all 20. So we have chosen these parameters as similar enough, relevant enough for in engine environment, but they are not identical to any specific fuel or gas and so on. So the velocity profile at the inlet, we consider the viscous effect. So you have a boundary layer, and we model the boundary layer with the Euler function. So the Euler function, you have a control parameters of the width of the Euler function. That's delta. We use it to represent the boundary layer thickness. That is 0.1 millimeter. So the splitter plate, we have a very small splitter plate near the inlet, separate the two streams. So they will not meet each other until they go to downstream of the splitter plate. And the gas and liquid velocity away from the boundary layer, 10 and 0.5 meter per second. So at the end, we get the Reynolds number based on the boundary layer thickness is about 1,000, but based on the stream thickness H is about 8,000, and the Weber number about 10. For this parameter, we just consider only one case, but we do a parameter study of the turbulence intensity at the gas inlet here. So for the simulation method, I use for the method to capture the interface, I use the VOF method. The volume of flow method is a very popular method right now to do interfacial multi-phase flow simulation. So here I just go to very basic step, 1,000 feet overview of the method. So you solve the color function. C is a color function. It follows the advection equation. So if you really want to have a conservative form for the advection term, then you have a leftover on the right-hand side. But for incompressible flow, divergence velocity is 0. So typically people just write 0 in this equation. So the VOF method in general consists of two steps. The first step is you want to reconstruct the interface. So let's say M is the normal vector of the interface. So based on the surrounding cells, the volume fraction, you need to figure out, what's the orientation for my interface. And then you also need to determine the parameter alpha that determine the position of the interface. Now you know the orientation, but where it's located in the cell that you have to determine based on the volume fraction. After you do that, you can go to look at one time step how much liquid or gas from your neighboring cells that is going to come into this cell. So if I have the velocity at my cell surface, go from left to right, I need to go to my left cell and see how much gas or liquid. For this case, if underneath here is liquid, I need to calculate this portion, and that will determine the flux going to the cell. And we use that to update the volume fraction at the next time step. Okay, so in this case, in the Paris code, we have used the split direction advection. So we advect in the X direction and in the Y direction. So a method developed by Weymouth and Yue, they indicated that if this term, actually you do not throw them away, set them to 0, you keep them, and that's a small numerical trick you can include in the advection that can achieve a mass conserving exactly to the machine error. So this is a method we use. So the method will be eventually conserve mass exactly. On the other hand, when you think about when you computing the volume of flow or the volume fraction flux into the cell and you achieve exact mass conservation, and what should we do with the momentum? So that's a problem that we have been looking at in the past few years, also in particular when I was still working with Stefan Zarsky in Paris. So in a typical way, you just solve the advection equation with whatever VOF method you use, but the momentum equation, in particular the advection term, you just do it in the general non-conservative form to calculate the velocity. So this will create a small problem because if you think about if you are pure gas cell and liquid cell, that will not be a problem. But if you are in a computational cell with the interface, you are computing the mass advection in one way, but then the momentum in a different way, then they can create a small problem. So that's why we improved the VOF method so that we when we calculate the momentum phi here, we also use the way to evaluate or compute it consistent with the Wolf method. Okay, so we have already computed the Wolf flux, the volume fraction flux, as I explained in the previous slide. So right now, what I need to do is to evaluate any other conservative variable like momentum, like energy, as a chaser associated with the volume of fraction flux. So at the end, no matter what I computed across the interface, then they will be consistent with the VOF. And the details can be found in our previous papers, and also the paper by First and Popinit. They use this idea to do a compressible version of VOF method. So this is a one test case. I saw the difference between the two, the conventional WRF and the mass momentum consistent WRF. The right column here is I simulated the two-phase mixing layer with different mass resolution. So as you can see that when I refine the mass, I can resolve the wave better and better. And for the M2 and M3 mass, the 2-5 masses, I get the rim pretty nice, and there's no breakup at this stage. But if you look at the coarse mass, they have a lot of breakup happening, but those are numerical breakup because you don't have enough resolution and so on. Interestingly, if you use the same mass resolution at M2, but use the old WRF method to resolve the same problem, and we see a lot of numerical breakup at the edge of the interface, similar to the coarse mass of the simulation. So that gives us the confirmation that if you have a high shear, unstable interface, using the consistent WRF method is quite important to get the right shape of the interface without introducing a lot of numerical error in the breakup and so on. So with that, I will move on to talk about the results. I first talk about the turbulent statistics and in the interface dynamics. So this is a movie showing general behavior of how does it look in the two-phase mixed layer, how the liquid interface become unstable, forming a wave, flapping and break and form the droplets. And the right here, I'm showing the vertical structures using the lambda 2 criteria and color the lambda 2 with a Z component vorticity. So when you see the red and blue color, that they tell you about the vortex rotating in different direction. And we see a lot of turbulence generated on the interface, in particular when the wave amplitude become grow, so you have flow separation on both upstream and downstream side. In the early stage, the interfacial wave approximated 2D, okay? And if I do a central plane cut, I can see the interface and see how the wave grow and propagated downstream. And the wave propagation speed, it follows the Demotakis speed. And that's basically you are moving in a moving reference frame, look at dynamic pressure balance. And if we shift the wave and also scale them with the Demotakis speed, we can see all these waves somehow overlap in the location that confirm they indeed propagate in the Demotakis speed and have a similar, self-similar wave pattern as reported in Hofner et al. Of course, at a later time, you can see the waves start to roll over, and that, of course, they will not look self-similar anymore. But at the early stage, they overlap pretty well. And after the wave gets stretched and flap, they will eventually break and form droplets. And in our paper, we have identified 2 different modes for the liquid sheet to break into droplets. The first mode is what we call the fingering mode. So when you have a liquid sheet on the edge of the liquid sheet, you form a rim. And due to Rayleigh plateau instability, at the edge, you're going to form a finger. And this finger gets stretched by the stream and eventually they break and form droplets. And the second mode is what we call the hole in sheet mode. And that is when small holes are formed inside the liquid sheet. When the liquid sheet is stretching and get thin, in the region they are very thin, they are going to break and form holes. And the holes expand and merge will at the edge or the boundary between two holes will form a ligament, and the ligament break and also form droplets. This rim instability and hole dynamics has been observed in other papers as well, and our simulation just have fine mesh enough to capture all these high level details. Well, we have also tried to characterize the turbulence in the problem. So because now we have a two-phase turbulence statistics, we need to use what typical called the favorite averaging that's represented by the tilde. So in averaging, we average in time and also in space in the z direction. So at the end, the mean flow is a 2D only change in x and y. And the z direction is a homogeneity direction, so we average upon that as well. So based on the averaging operator, we can do that for the momentum equation and also the kinetic energy equation. In the simulation, we collect data for also the high order statistics so that we can eventually look at the TKE budget in the flow. So this is the mean flow, the mean volume fraction, and also the streamwise velocity. So if the liquid break into droplets, so the mean liquid volume fraction will drop immediately to be very small values. The color will be very light, hard to see. The blue part here is the unbroken, basically is unbroken liquid core that the liquid volume fraction is always 1 over there. And in the mean velocity, we can see the gas jet. And the Reynolds components, we can see that both the gas mixing layer and the gas liquid mixing layer are the location where we have a large turbulence generated, and the gas liquid mixing layer is have a higher turbulent intensity, and the location for the larger values we observe here is about the wave when they grow to the amplitude comparable to the gas stream, so have very strong interaction with the gas stream and breakup start to happen. So we can also average also in the y direction altogether. So at the end, get the 1 DTKE budget in the x direction for the mixing layer. So this showing all the different terms in the TKE budget: the advection term, pressure term, turbulent diffusion, viscous diffusion, dissipation and production, and also the contribution of surface tension. So surface tension at the gateway pressure is the will give you a lot of noise because you have a surface for the droplets everywhere. So we have subtracted the capillary pressure portion basically from the pressure term, and then we get the pure pressure contribution to the TKE budget. So you can see the dominant term is the production and the advection term in the near field. And the dissipation has a lag behind. They do not get to the maximum value until a further downstream. So at the breakup moment, and you have a lot of turbulence generated, but they are not dissipated until a little bit further downstream. So look closely to the turbulence statistic. One purpose is to answer the question is that, do we really resolve the turbulence statistics? Now, because the VOF method and some other interface capture method improvement, and also computer power, now many people claim they can do a high fidelity simulation or even direct numerical simulation for atomization. So indeed, the question is that what you need to resolve enough to claim that your simulation indeed high fidelity. So this is an easy question to ask, but not so easy to answer, because full affirmation of that resolving order scale cannot be done until you do a grid refinement study, as what we learned from our CFD course. So we have played this very expensive game by varying the mesh from the M2 to M3 mesh, that in which the cells are varying from 25 micron all the way to 3 microns. So for this periscope right now, we use a uniform mesh, so number of cells will go up rapidly from 8 million to all the way to 4 billion. So you can see we have to use more computational cells, cores, processors, and also the total CPU hours get increased dramatically when I refine the mesh. So not until we reach the very fine mass using a 16,000 CPU cores to run a simulation for months, we don't get to achieve a more or less converged result for the dissipation. So you can see for production and the advection term, even the M2, M1 mesh already do a pretty clean job. So here in the figure, I use the same color for the same term in a TKE budget, but different line pattern represent a different mesh resolution. So in the advection and production, we are comfortable, even the M1 and M2 mesh do a reasonable job. But for the dissipation term, you can see the M1 mesh results significantly under predicted value, and not until the M2, M3 mesh we get kind of a converged results. So this gives us an important lesson that the turbulent dissipation is the most demanding term, even in the two-phase turbulent flows when you have atomization going on. And when we look at the dissipation distribution over the XY plane, going from 1D now back to the 2D mean flow, average 2D flow, we can see indeed though the turbulent dissipation is maximum in the 1D in the about x equal to a h, that's the height of the stream, but indeed in the production region you do have also very high dissipation, and you need a very fine mass to capture the right value of the maximum dissipation in this area. And with that dissipation rate, we can go back to the classic theory of Kolmogorov scale estimate to estimate what the Kolmogorov scale is for this specific case we study. And we look at it, it's about 3 to 4.5 microns. And the fine mass we have used delta X, the cell size is also about 3 micron. So we this is kind of confirmed that we have used a fine enough mass to capture both the interface dynamics and also turbulence. So we can claim our simulation indeed is a high fidelity. So with that, I want to move on to the next results I'm going to talk about is the impact of inlet gas turbulence. Why we care about the turbulence at the gas inlet? So we have a gas liquid mixing layer. In the simulation, we only consider the flow outside of the nozzle, but there's a lot of things going on inside the nozzle. On purpose or just by nature, when you have a high Reynolds number flow, internal flow, they're going to have introduced some turbulent fluctuation. So I said, this is in the experiment of a Marta Setel. They have also shown that if they introduce some turbulence at the gas inlet, they see a shift of the most unstable frequency. So this is spectrum of the interfacial height. So they can see that if they add in some turbulence, that's the red line, and the dominant frequency shift to the right. So, but still a lot of downstream effect. What happened to the spray formation is still not known in that paper. So that's kind of inspire us to look into this problem. And also we found out that if you can see that changing the turbulent intensity a little bit at the gas inlet can change the spray downstream a lot. This can eventually become a spray control technique. In the simulation, we're going to introduce the velocity fluctuation based on the digital filter approach. We add in the inlet boundary condition, so introducing the fluctuation, and that's a spatially and temporal correlated fluctuation to mimic the turbulence effect. So this is a summary of the cases. So we have considered two different domains. So W represent the wide domain and the N represent narrow domain. So for the length and height of the domain, Lx and Ly, they are 16 and 8 times of the stream thickness, so they are fixed. But for the domain width in the Z direction, the narrow domain is 2 and the wide domain is 6. And we have do a parameter study for the turbulent intensity at the inlet. So different I values, and when I equal to 0, that means I don't have any fluctuation at the inlet. And with a large value, that means I have a strong turbulent intensity at the inlet. And we have done this simulation and text MP. In each of the W case, it takes about 20 to 25 runs. Each run takes about 2 days running the computers and using about 3,000 or 1,000 cores. and the total computer time is that we use more than 400,000 node hours. So to just check if the turbulent fluctuation we introduce at the inlet is correct, we go to a little bit downstream of the nozzle exit and go to measure the mean velocity over there. So if you look at the mean streamwise velocity in the gas and the liquid, they for all the cases we study, they are very similar, almost identical to each other. But if you look at the Lumen square or the normal stress, and you can see the difference of them, of different cases inside the gas. So for the case of W2, that's the maximum turbulent intensity we have considered. So the Reynolds stress will not be uniform inside the gas layer. They will first increase like in the typical boundary layer to a larger value and then come back to a constant. So we just pick the value at the center of the gas inlet, and that is the value we use to measure the turbulent intensity I. So the I value you see 0.1, 0.13, that means the turbulent intensity measured at the center of the gas inlet. And this shows the general behavior of the two cases. So on the left, as you can see in the gas velocity here is pretty clean. That means there's no fluctuation. On the right here is the video here. We introduce the fluctuation. You can see the turbulence and so on. And the impact of the inlet gas turbulence on the interface can be seen immediately with introducing turbulence. I see the wave become more unstable, see a lot of the wave develop much faster and closer near the nozzle, and the downstream pattern also different. Interestingly, we see less droplets form when we injected turbulence, and also the wave, not only the longitudinal wave, also the transverse modulation are impacted by the turbulence as well. So we're going to look at each one of them individually in sequence. We first look at the longitudinal shear instability. So if I go to a location just near the nozzle exit here to match the high edge and collect the time signal, that's what you see in this figure. Okay, so for different cases, if you have a higher turbulent intensity, the oscillation is bigger, if the amplitude is bigger, but if you have the laminar case, the amplitude is much smaller. Okay, so the injected turbulence not only impact the amplitude, but also the oscillation period. So if you, or frequency. So if you do a Fourier transform of this time signal, this is spectrum. And if we just we look at the three Y domain cases, W0 to W2, we can see the peak of the spectrum, that the dominant frequency will go to the right. So that means it's increasing as the turbulent intensity increase. And that's summarized also in this figure that we show how does the longitudinal frequency increase with the turbulent intensity, and compare also with the experimental data by Martas et al. So generally we capture the trend, the simulation and experiment are similar to each other, that when you increase the turbulent intensity, the longitudinal dominant frequency increase approximately, I would say, like a linear. And the question is why? What happened? Why, when we add in turbulence, even with a quite small amplitude, the intensity like a 3% of fluctuation, a 6% of fluctuation, it will introduce a significant increase of the dominant frequency? To answer a question like that, we have to go to the linear stability theory, because this is a more typical normal mode analysis for parallel flows. I'm not going to spend a lot of time explaining the details. So basically, this is we solve the Euler-Sommerfeld equations, and with the code developed by Otto et al. So the Euler-Sommerfeld equation need to match the boundary conditions in the far field away from the mixing layer, and also at the interface, capturing both velocity, stress, continuity, and also the kinematic condition. And with a one basic velocity profile you assume, then you can solve these equations and get the instability, this unstable mode. The basic velocity profile, due to the existence of the separator plate, we do have a velocity deficit, and characterized by a parameter delta D in this figure. So here, the blue lines is the simulation results just downstream of the separator plate. And we do see a velocity visit over there. So in the base flow we use in the stability analysis, we also need to model that to just be consistent. So for the stability analysis, you can do the temporal analysis that you give a wave number and to look at the complex frequency. And also the spatial analysis will be have given a frequency and try to get the complex wave number. And the spatial temporal analysis will give, just assume both the frequency and the wave number a complex number. So in this figure here, I'm showing the omega I equal to 0. So that's basically the spatial stability results. And when we don't have surface tension, that's the purple curve here. I only see one branch. So that telling us that this is a convective instability, and you can go to try to look at the maximum growth rate. I'm sorry. So here I forgot to mention. So the x-axis, the real part of the wave number, and the y-axis here is a negative imaginary part of the wave number. So we get a spatial branch that is due to the shear. That consists both of the inviscid and viscous contribution to the shear branch. If we introduce a small surface tension, can see the appearance of additional branch, and that's controlled by the surface tension. If I keep increasing the surface tension, they will change the shape of the two branches. That you will form in what we call a settle points, as you can see here. So if you look at when the omega I equal to 0 cases, that you see the pattern of the branches change from a single branch to multiple to two branches that can pinch. Then we can look at the branches and in different omega I. And if a settle point arises, that is a location where d alpha r, so that's a group velocity equal to 0. That means the perturbation can now propagate in both downstream and upstream. And the instability will transit from the convective instability to absolute instability. And this is settle point will determines the most unstable absolute mode, and there determines the frequency and so on. So when we don't have the turbulent intensity for I equal to 0 cases, we use the stability analysis and can predict the frequency and compare the simulation result. That's the purple line. So you see, the peak predicted by the simulation and by the theory, they agree reasonably well with each other. So then now we come to why the turbulence will make the dominant frequency increase. To incorporate the effect of gas turbulence into the linear theory, we can use a very simple turbulent viscosity model. So mu star here is effective viscosity contributing, it consists of the gas viscosity originally and also the turbulent viscosity. And for simple shear flow, well, we can use a simple way like showing this formula here to estimate the turbulent viscosity. And with that, we can see that how does the increase of the inlet gas turbine intensity change the effective Reynolds number and the viscosity ratio in the linear theory. And with that, we see that the settle point for the two different cases, for laminar case and for the turbulent case, they shift to the right. So the increase of turbulent intensity caused the settle point in both the wave number diagram, also in the dominant frequency omega r, all shift to the right. And that this simple model predicts the trend pretty well. But as I saw in our paper and also in Martha's paper, that this simple model still kind of underpredict the frequency, and that requires some further investigation in the future. Now, we say that, well, you include the turbulence and change the dynamics of the shear instability in the frequency, but why that's important? If I'm going to the downstream just collect droplets, would that matter how fast, I mean, what the frequency of the waves I will see. But actually, that's really important because the longitudinal shear instability creates oscillation of the interface in time. If you stand it in the one location, look at it, you see that the gas will first decelerate toward the gas and then accelerate toward the liquid. And in these cases, that will trigger the Rayleigh-Taylor instability. And that's the reason when we see the transverse modulation in the interface. So I took a top view of the interface. You can see the case that here, when the interfacial wave is still pretty much, the line is still a straight line, but the high already showing some transverse variation. And that's created actually due to the Rayleigh-Taylor or the baroclinic torque. When the interface is decelerated upward, you have the torque make the small perturbation become more unstable, and that creates a transverse variation. So assuming this is indeed the dominant mechanism, we can use the Rayleigh-Taylor theory to predict the most unstable wave number. I see here that this is a growth rate as a function of acceleration, wave number, and also density ratio and surface tension. So the most unstable wave number happens as the maximum growth rate and predicted by KT. And this most unstable wave number will depend on the acceleration. And this acceleration, as we have mentioned, the interface acceleration, is triggered by the longitudinal instability. So we can use the longitudinal dominant frequency we predicted in the previous slide to estimate what the acceleration is. So with that, we can plug it back in and get the estimate of the most unstable wave number. And we found out that this will be proportional to the longitudinal most unstable frequency. And we want to confirm this simple theoretical scaling relation we have obtained. So we go back to the simulation and go to each x and t, each time and x location. I go to look at how does the interfacial high vary in the z direction and do the Fourier transform and get the wave number spectrum and pick the maximum wave number and then end up with this xt diagram for the maximum wave number. So we can see a lot of lines on this wave diagram, and that's the longitudinal wave. So we found out that the transverse instability development is related to the longitudinal instability. At the location when the longitudinal wave pass, you get those strong transverse variation happening. And so if we want to compare with the theory, we have to only collect the maximum wave number on the longitudinal wave location. And with the left figure showing the laminar gas inlet and the right is the turbulent gas inlet, you can see not only the longitudinal wave time period of frequency change, also the Kmax, the most unstable wavelength also change. And that's summarized in this picture here. We're showing how does the transverse wave number increase with the turbulent intensity at the gas inlet. And so comparing the simulation and the theory and simulation have some discrepancy. Also, again, we capture the trend reasonable, but there's still some discrepancy. And that may be also related to the fact that when we estimate the acceleration, we have to use a fixed length scale. We change the frequency, but the fixed length scale. But actually, that length scale to characterize the acceleration may also change with turbulent intensity, and that should be improved in the future. So the change of the transverse instability will also have an impact on how does the liquid sheet going to break. When we have a laminar gas inlet, the wave number, transverse wave number is low, so you only form like a 1 or 2 wave in the transverse direction, and the wave got to form a long liquid sheet. So at the end, they break more in the hole in sheet mode. So you form a lot of holes, and the holes merge in, break, and form droplets. But on the other side, when you have turbulence at the gas inlet, you increase the wave number in the transverse direction. So we form more waves in the transverse direction. Then at the end, you don't get to form a long liquid sheet, and the and the liquid sheet eventually break in more like a fingering mode. So you form in the fingers and the finger break and form droplets. And that also is, you can see that if a fingering mode, you form smaller number of droplets compared to the holes in sheet mode. And that we will also expect to see the turbulence intensity will also have impact on the size distribution of the droplets. I also would like to mention here that the breakup here will depends on the material solution. In fact, of the hole formation needs a careful consideration as well. So the different breakup mode also have impact on the turbine statistics. Due to the time, I'm going to skip this slide and show the job size distribution. So one take-home message for this study is that you will generate a lot of joblets, and then joblets will follow different distribution function. As you can see here, you really need to refine the mesh to capture the right shape of the job size distribution. And we realized that when we use the fine mesh, we found out that the distribution for quite a big range over there seems to follow the log normal distribution. And when we change the turbulent intensity at the gas inlet from laminar to a very turbulent, we see less droplets are formed, but they are forming closer to the inlet. So the turbulent fluctuation added at the gas inlet not only change the number of droplets formed, also the spatial location where they are formed. So I'm going to skip these slides and give a summary. So in this talk, we have talked about high fidelity simulation that can accurately capture the interfacial instability, so that we believe the spray formation process is well captured. And the destabilization of the bioliquids starts from the longitudinal shear instability, but which then later trigger the transverse moderation due to the Rayleigh-Taylor instability. And the interfacial waves develop and form liquid sheet, and they can break through a fingering mode or the hole in sheet modes. When you have inlet gas turbulence, that they can have a big impact on the interfacial instability, making the shear instability dominant frequency increase, and which also increase the dominant wave number, and eventually change the breakup pattern of the liquid sheet, and also have impact on the job statistics. And finally, I would like to emphasize again, the turbulent dissipation is the most demanding term. So you would like to make sure that's well captured to claim the simulation is the high fidelity. So we have developed a scaling relation, but in future work, there's also a lot to do to fully confirm this scaling relation for the interfacial instability. We have a look at a relative simplified configuration, have a liquid layer on the wall, but in a lot of Airblast configuration, atomization configuration, you have a gas on both sides. In that case, there will be asymmetric instability mode to look at. And understand this, all the physics involved in Airblast is trying to help us to get to the normal design of nozzle geometry, and also in the cases when you have a high temperature engine environment, we need to incorporate the phase change, and that's what we have been working on. For example, you can see in this figure, we're simulating an evaporating droplet when it's breaking up and also evaporating. And finally, the DNS results are very interesting, but also very expensive to obtain. How can use them to develop subgrid model is what we are going to investigate in the future. So with that, I would like to thank very much for your attention, and I will answer any question if you have. Thank you.
Thank you very much, Stanley. It was a very good talk. With that, if you do have any questions, you can either type them in the chat, you could raise your hand, or just unmute yourself, turn your camera on, and you're welcome to ask questions. While people are starting to do that, I do have one for you, Stanley, to get the ball rolling.
Okay.
In your, at least your initial simulations, your splitter plate was a very small thickness, correct?
Yes.
In physical terms or in an actual system, that splitter plate is going to have some finite thickness that would also cause the flow to change almost like a backward facing step. And I'm wondering, how would that be incorporated into your model?
Yes, that's a very good question. So when we look at a mixing layer in textbook, if you don't have this splitter or separator plate, you have a cold flow case, you always have a convective instability. That's known for a long time. And you will not have the absolute instability until you have a little bit counterflow. And this separator plate create a velocity deficit in the base flow that contribute to the transition from convective instability to absolute. So if you have a small separator plate, when I say the thickness is small, what I mean is that compared to the boundary layer thickness. And people figure out that, yes, that will have some effect, but the specific thickness will be not very important. But when they become comparable to the boundary layer thickness, then you will have flow separation and so on. Then they will indeed change the dynamics. That will make the stability analysis, I would say, more complicated. But simulation, we can incorporate that, assuming we have fine enough mass. But you're right. For the cases like those have absolute instability, the perturbation propagate upstream as well. Sometimes they can even push the interface back inside the nozzle and make things very messy.
So I see, I think Macron, you had your hand up before Bala. So Bala, I'm going to defer to Macron if you could ask your question.
Thank you, Professor Handel. Thank you very much for a great presentation, Dr. Ling. It's very interesting to see that dissipation takes longer to converge, perhaps not surprisingly. However, my question relates to the convergence of droplet size PDF. And well, the two-part question. One, with your M3 mesh, do you see a converged PDF for the droplet distribution? And the second part is, you're using VOF, so I'm assuming you have some sort of a cutoff of 2 or 3 cell sizes. Anything below that is probably. Can you elaborate on what your mesh cutoff is for the size of droplets which you count as physical?
Yes, very good question. So even if the M3 mesh, we do not get converged droplet size distribution for a very tiny droplets. So in the Wolf method, the cutoff length scale is my cell size. So any jobs smaller than cell size, I will not be able to resolve, that's for sure. But even the jobs close to the cell size, the formation will not be very accurate as well. So in such a case, I would say our hope is that we get converged statistics for the large droplets we have formed. And if those droplets, if you look at the number distribution, they're always small, but if you look at the mass fraction or the surface area fraction, they may consist majority of the surface or the volume. And for those cases, I think we get reasonable agreement or convergence with the fine mesh.
I see. Well, following up, so this issue of really reaching the high fidelity limit for atomization. So would you comment that on a little bit if the droplet distributions are still not converged?
No, of course. That's why I say high fidelity instead of direct numerical simulation. That claim I resolve every single scales in the process. I understand. So the problem. So think about in the single phase turbulent flows, what you call high fidelity simulation. You call LES also high fidelity. You look at the energy spectrum, you're not resolving the whole spectrum, but you cut off some small energy contribution from the small eddies. So for the sway formation, it's a similar kind of idea. I will have to do some cutoff to ignore some small droplet formation. But if those small droplets, they contribute to only a small portion of the surface area, then I would say my cutoff is reasonable and still can be claimed as a high fidelity. But if you say no, I mean, this droplets you cannot resolve consists of the majority of the total surface area, because surface energy proportional to surface area, then I think then you cannot claim the simulation's high fidelity. In long term, we do this very expensive simulation is also trying to develop subgrid model for the droplet formation. Even in the case I saw here, when we simulate only one droplet, I put all my money into simulating one droplet. They also have droplets that I will not be able to fully resolve. And but if we can resolve majority of the surface area, that will be the physics or the data I can use to mine to develop a subgrid model that if you use a coarser mesh in the future, you can also mimic the breakup process reasonable.
So thank you very much, Macron, for your question. Bala, why don't you go ahead?
Yeah, Stanley, great talk. Enjoyed it very much. I have a question that goes along what you said in response to Ted's earlier question. My understanding is that for absolute instability, the base flow must have a backward velocity. So if I understand you correctly, if the splitter plate is infinitely thin, then you only have convective instability. Therefore, you need some, is that a firm conclusion that if not, do you have a backward flow in your base flow? What's the source of this absolute instability, the pinch point?
Yeah, sorry, I probably gone a little bit fast over there. So if you look at the first figure I'm pointing at here, I believe the pinching point we see here is not due to the counterflow. In our study here, I'm sorry, you need to rotate your head a little bit, look at here. So this is a gas velocity and the liquid velocity. We have velocity physics, but we never have a negative velocity. Okay, so we don't have the counterflow, and we don't think the counterflow is the reason for the transition between convective to absolute instabilities. Instead is that we believe that's the surface tension. That's also mentioned in Matas et al.'s paper as well. So if you have a no surface tension, Weber number go to infinity, I only have one shear branch. When I increase the surface tension a little bit, I can see another branch showing up. The green branch, the shear branch is still here, and have a new branch showing up. And I further increase the decrease Weber number, increase the surface tension. Now you get the blue two branches, change the orientation. That's an indication of pinching happen. So when you have a surface tension, the capillary wave can propagate in both directions. So if they can overcome the liquid velocity convection effect, then you also have absolute instability. And that's how we determine the most unstable frequency in the problem.
Thank you.
So I guess, Charles Petty, you have your hand up. You can go ahead and unmute yourself.
Oh, thank you. Can you hear me?
Yes. Yes.
I want to just make a comment and ask you a question that you used looked at some statistical methods that you showed us. And so my first comment is that the rental stress is an ensemble average. It's not a time average. And so, and when you were looking at the turbulent kinetic energy, you showed us a statistically stationary equation. As if it were statistically stationary. But do you have any evidence at all that this complex flow field is even close to statistically stationary statistics, so that you could so that you can present I don't remember, I think it was slide 15 or something like that.
Yeah.
You showed this. So my question is when you're doing this, I know you're after something that you're doing, but what is the logic for you to take that step?
Okay, a very good question. So for the two-phase mixing layer here, we have open channel, so inflow, outflow. So when the liquid coming in and break, and after the transition phase, I do get to statistically stationary state. So we can basically pick a location or look at the total kinetic energy, see how it changes over time. And we do see the fluctuation, and the mean will not change in time anymore. So that's why we believe for the mean flow, we can throw the time away. And I agree with you that it's important that for the kinetic energy or all the turbulence statistics kind of average, and we have to do it until we reach this steady state. But we do have check it. We look at the time evolution of let's say dissipation or the whole domain and see how it changed over time. We increase and then reach a plateau, and then we only do the averaging at the plateau.
So a corollary of my comment is that you, if you're going, so you're just taking information that's coming in and coming out. Is that what you just said?
Yes.
Okay.
Right. Yes.
That's fine. That's okay. That's not. Yeah, go ahead. Go ahead.
It's not a periodic boundary condition though, and just keep going on. But you're right. I mean, I kind of fix my camera here and collecting the data. Yes.
Yeah, I forgot what I was going to say.
So,
I'll come back.
Okay.
I'll come back in just a minute. Okay,
So
I got to
Rodney,
look at my notes.
Why
I
don't
got to
you go
look at
ahead?
my notes. I'll come back.
Okay,
Okay.
I'll come back to you, Charles, after Rodney's question.
Hi, thanks. Thanks, Stanley. I enjoyed your talk. It's very, very interesting. I did have a question about the subgrid modeling and you had the particle size, the droplet size distribution that you're getting out of your simulations. I'm wondering if you've also looked at particle velocity distributions, because one of the important things that goes into subgrid modeling LES, you need also the velocity of the droplets when they're produced. You have the data. I'm wondering if you've looked at it, and especially conditioned on size. Are you able to get that kind of data? Have you looked at it?
Yes. I don't get a chance to talk about that. But for example, in this slide here, we look at the ejection angle distribution of the droplets generated. So I agree with you. So if we want to develop subgrid model, I not only need to tell you how many droplets going to form, what's their size, how does the size relate to the velocity, and also
Right.
angle will be relevant. But you're right, we have not looked at the velocity in detail, but we realize that the dynamics, how to characterize the droplet dynamics statistics also important developing the subgrid model.
Okay, yeah. So we're developing models for that for gas particle flow. So it'd be interesting to have some actual experimental data to look at. So thank you.
Okay, thanks. We would love to know more about that.
Yeah.
What do you develop?
Okay, so Charles, I'll go back to you if you have your question ready.
Yes, you discussed the dissipation a little bit.
Yes.
And the dissipation in annular flow, a much simpler flow than what you showed us, could be negative, and that's been shown a number of years ago, and even Pope makes that identification in his book 20 years ago. So I was wondering if the dissipation. Do you take so you have the eddy viscosity also in your presentations, and so does the mu become negative when you have a region in your flow field where you want to make the dissipation positive?
Actually, in my case, I have not seen any cases I have a positive dissipation. So I mean, I can share my screen again. So this is the dissipation distribution in the 2D flow. But I don't see any cases in our case that here we have a positive.
So in your dissipation, do you always get a positive number for dissipation?
I mean, it depends on how do you define it. For our way to define the dissipation is always negative.
So the mu with a bar over it on the right hand side, is that your eddy viscosity?
Oh no. That's just the mean viscosity.
So that's
between the two
that's the
phases.
objective viscosity?
That's the viscosity. When I say the mean viscosity, is that because I have a gas and liquid, so I need to take the average of that.
Okay, when you, I know,
But that's
when
not
you,
the turbine viscosity, not the.
that's not the turbulent viscosity.
Yes,
Okay.
yes. So sorry about that. That bar is not, does not mean the average viscosity in time and estimate the turbine viscosity.
So is that the physical viscosity of the fluid that you're working with?
Yes,
Okay, so it's positive always, right?
yes.
Okay. Thank you. I thought you were, well, thank you. That's good. Have you ever seen in you've never seen in your experiments, a dissipation which went negative? Is that correct?
No,
Is that what
not in
is that
this
what you're saying?
Yeah, yes, I have not seen in this case.
Okay. Thank you.
Thank you.
So Rodney, I'm assuming you don't have another question. Your hand is just kept up. If you do have questions, certainly unmute yourself. Thank you. Any other questions?
Actually, I have a follow-up.
Yes, go ahead, Akron.
Professor Handel. For collecting the turbulence statistics, you said that you're essentially taking essentially a box which is far away from the inlet, right?
Oh no, I mean I do everything for the whole domain. for the whole domain, I average in the z direction, also in time and calculate statistics.
I see. So could you please comment on whether it's better to maybe take the statistics away from the inlet where you have some convergence?
I mean, I try to measure everything. If it's not useful, I mean, you believe, oh, need a nozzle, you're not equilibrium enough. I mean, then it is what it is, right? I mean, you can then focus on the downstream to look at the energy spectrum. If you believe you need to wait for in the downstream to see the turbine to fully develop, that's fine. But when I do my simulation, I collect all the data. I do the average in time and space for the whole domain.
I see, and maybe sort of circling back to the other comment, would you say in that case that the ensemble averages would correspond to the time averages?
For my case, I would say I'm just doing time averaging.
Okay.
And I do time averaging until the statistical stationary state has been reached.
Okay, thank you.
So we have one more question from Rahul Corneru. You can go ahead.
Yes. Hey, Stanley, very interesting talk.
Thank you.
So my question is there a reason for not using Basilisk, given that it has AMR capability that could have relieved some of your meshing constraints?
No, I mean, Basilisk will probably do similar things. Just when we started this project, we work on the Paris simulator code, and you can see that I tried to use a improved version of the VOF method. And at that time, that method is not in Basilisk. It's true. Right now, probably I can redo everything in Basilisk to use the AMR and even go to push another level of refinement.
Okay, great. Thanks.
All right, I think that's it for questions. Stanley, I want to say thank you again. It was a very interesting talk.
Thank you.
And I'd also like to let everyone know that we will be reconvening probably in September. Look for